another topic, but close to previous. Namely, I will speak about the algebras generated by graphs, namely locally simple algebra and AF algebra, which generated by graded graph or so-called Bratley diagrams. And I want to speak mainly, there are many questions close to this, but I choose the following, namely the problem about the invariant and so-called compatible measures on the space of passes of this graph from one side, a problem about characters and trace on AF algebras from other side, and at least two things. A problem about the so-called projective limit of simplices. This is very nice pure geometrical topics, which now it happened that it's completely adequate to previous. And I will mention only shortly connection with theory of boundary of Markov chain. So maybe I will tell about these three equivalent theories. The first theory is just the theory of the paths of shortly Bratley diagrams. Second theory, characters and traces of AF and other algebras, and the projective limits of the simplices. Let me remind you what does it mean, graded graph, Bratley diagram. It's very popular now, and I want to say that this is one of the, first of all, simplest object, and from other sides, very, very important in many theories. So I consider gamma, which is n is naturals, graded graph, which means that first of all vertices has index from natural numbers. Say the first vertex, empty vertex, has 0 if you want, and then you have some levels. Well, I will write the simplest graph, Pascal, but this is also non-trivial, but one of the first example. The additional assumption that edges join only the vertices which has adjacent levels. So edges can be join level n and n plus 1 only. I consider simple graph without multiplicity, but multiplicity is possible. Moreover, it's very important. But I will, in order to have shortest way to formulate the theorem, I consider only graph without multiplicity. Now also, it has no vertex which has no follow. So each vertex has follow, and each vertex except this one has previous vertex. That's all. And it's difficult. So this is what people call Bratley diagram. Bratley is mainly specialist in operator theory and statistical physics. Unfortunately, he died recently. And his idea was to use this picture in order to construct the algebra. It's very strange that such a simple object can generate canonically algebra over, say, complex number or some fields. And this algebra, in a sense, rules by property of this object, namely A gamma is inductive limit of, say, AN, algebra AN, and each AN is the sum of algebra of matrices where Ki, some order, belongs to some set of integers, say AN. So the rule how to construct this algebra looking on this graph is very simple. Each vertex on the level n corresponds to matrix algebra M something C, and this order of this matrix equal to the number of passes which goes from the beginning to given vertex. So it's uniquely defined algebra, matrix algebra for each level. Now we can consider direct sum of such a matrices, and this is nth algebra. Now the embedding an to an plus 1 is also very simple because it rules by these edges. For example, these edges means that this matrix algebra embedded to this matrix algebra simply as block of algebra which has at least more order than this, because order of this algebra is sum of orders of this. So this algebra is algebra generated by these two summands, which is block diagonal blocks. If you have vertices, so you have to consider tensor product of this algebra to itself correspondingly to multiplicity. That's all. And so you obtain so-called locally simple algebra. So this is infinite dimensional algebra. Of course, this is algebra with involution. You can consider sister norm. And of course, you have sister completion of this algebra. And such an algebra called AF, approximately finite dimensional algebra. And class of this algebra is very important, and I will not speak about this as a separate topic. So this is one connection of such a guys with this. Moreover, one of the main theorem in this direction, this theorem by George Eliot, who proved that type of these sister algebras, so this algebra uniquely defined up to isometry and isometry, involution isometry, up to a type of this graph. So roughly speaking, the type of this graph uniquely up to isometry define this algebra. This is simple part of the theorem. But moreover, if you have such an algebra, then you can define this graph up to approximation. So roughly speaking, the difference between various graphs which corresponds to this algebra simply approximation. Of course, for example, if you forget some levels, you didn't change limit algebra. I will not speak about in more detail, but what is important that asymptotic property, or it's better to say property of this algebra, which can be very complicated, and there are a lot of good examples of AF algebra, depends on asymptotics of space of passes of this graph, and this is one of the main objects in my talk. So let's define T of gamma. This is a space of passes of graph gamma. By path, I mean every time infinite path, which started at the top vertex and goes to infinity. And then it's clear that this is inverse limit of the following sets. You can consider path up to its beginning. And so this space could be considered as profinite space. Yes, because each path, roughly speaking, the sequences of the edges. Edges, not vertices. It's important if you have multiplicity. So you have a set of edges, and in this infinite sets, as a space of infinite sequences has weak topology of inverse limit, and this is, of course, in general Cantor set, and so you have canonical object, if it's clear, I hope. So this is Cantor set. We fixed some important things. So first of all, there is a tail equivalence relations. Namely, two paths xi and xi prime, this is two paths in our space, is equivalent if there exists n such that xi plus n equal to x prime I plus n. Roughly speaking, these two paths coincide starting from some place. So the difference only beginning of these paths. So this equivalence relation gives you so-called filtration. Filtration, which means, let me define A0. This is a set of all Borel subset of space of passes. Then next one, A1. This is a set of all passes which ignore first level. So this is a set which contain with this pass also this pass. So in a sense, this is a sigma field of the Borel subset which contained with the path together with path which corresponds to this equivalence relation on the first level. The same with second level, and so on. So this is decreasing sequences of subsets. And it will play a very important role in next part of my talk. Now, the main object will be measure, Borel probability measures on the space of the passes. So, what does it mean? Well, I repeat once more, this is Cantor set. On this Cantor set of passes, you have Borel sigma field, so you can define probability measure. Roughly speaking, this is probability measure on the space of sequences of the edges. And I will consider such a measure. So up to now, I will not use any denotation. So this is our object, measures on T of gamma. And I want to say about some special kind of measures. Central measure. So suppose you have some measure mu on the space of passes of this graph. I will call that this is central measure if this measure invariant with respect to change of the beginning of the path. how to say more concretely? It means the following. Suppose you have some set of passes, class equivalence of the passes, which coincides starting from some point. And look at the conditional measure on the beginning of this pass. Measure is central is all this beginning of the passes has the same probability. Or it's possible to say there's a conditional measure is uniform on all these things. And this is true for all n. Let me say the simplest example. By the way, it's important to have example. The simplest Bratley diagram is the following. Non-trivial, of course. I must say about this, because everybody knows what the AF algebra corresponds to this graph. This is nothing more than infinite tensor product of algebra of second order. Indeed, if you have here, you have M, here you have C plus C, here you have M2C plus M2C, and so on. So roughly speaking, this is a tensor power of this. So in this case, all passes is nothing more than sequences of 0, 1. You go to the, say, this direction or this direction, and so on. Say, directly in vertical 0 and to other side 1. So this is sequence of 0, 1, and central measure in this case is the same as Bernoulli measure. It means that for each vertex, all these guys has the same probability. So central measure for given graph plays important role, namely theorem.
Sorry, so there is a unique central measure.
Sorry?
Does this define a unique central measure?
No. This is a class of measures. For this case, in a sense, you are, in this case, it's only one, indeed. But in general, this is our problem, to describe all the measures. Theorem. Each central measure define trace on algebra which we define. And vice versa, each trace, I think you know what this means, trace on sister algebra. Linear functional, which has property and positive in usual sense. Space, yeah?
Could I ask you about one more example, the Young's lattice?
Yes, of course, I will tell about this main example, of course. So, central measure, define, I tell you how to do this, trace on this algebra, and moreover, each trace on this algebra, define measure on this graph, very different object. Namely, if you look at this space, I want to return back to space of sets. It's better to... If you have space of all continuous function on the space of passes, this commutative algebra, yeah? Of course, this is subalgebra of AF algebra. In a sense, it's called Gelfand-Zetlin algebra. So, of course, it depends on the graph. And if you have the same algebra and little change the graph, this algebra also will change. But nevertheless, for given graph, this is commutative algebra. If you have trace on this algebra and restore, restrict this trace on this subalgebra, commutative subalgebra, then you obtain, of course, measure on the space of graphs. And it's easy to check that this property of trace immediately gives you centrality, which I define. So the bijection is clear. If I have trace, I have measure, which is central. Vice versa, not so trivial. If you have central measure here, then it defines some linear functional on here, and it's not difficult to prove that this functional can be extended from this subalgebra to all algebra. And now we obtain very important tool in many problems of functional analysis and algebra and so on, because how to describe all traces is a very non-trivial problem. So we have to approach. From one side, we can construct this Bratley diagram to look at the space of passes and try to solve really combinatorial problem. I will tell about in more detail. Combinatorial problem, how to describe set of all central measure. From other side, this gives you the recipe to find traces. And partial case, if this algebra is indeed group algebra. So suppose you have a group which is locally finite, which means that this is inductive limit of finite groups. It's clear that in this case, this group algebra of group will be inductive limit of and we just obtain this situation. Our lowest example is G is infinite symmetric group, and this group is nothing more than inductive limit of symmetric group of finite order, and we obtain such a problem, and this is answering the question. In this case, it's a deep fact that Bratley diagram for this example is so-called Young graph, which is more complicated than Pascal graph, but let me write down. This is a graph of Young diagrams. I think that now it becomes very popular for many reasons. So nth level of this graph is all Young diagram with n cells. And Young diagram is nothing more than finite ideal of the lattice Z plus Z plus. This is very non-trivial diagram, and we have a very nice connection. You can define this diagram, it's clear for, say, for school children, and the question is how to describe all invariant measure on passes of this graph. What does it mean, path? Path, this is so-called Young tableau. Namely, this is not simply diagram, but diagram with naturals inside all cells, which increase by rows and column. And if you have such a diagram, then you have path, because these numbers show you how you go through the graph. So space of Young tableau is nothing more than space of Young diagram. Centrality means what I told. If you have some random Young tableau, then the conditional probability of all diagram with all tableau with given diagram are the same. This is the definition of centrality. From other side, this gives you this trace on this algebra. But what does it mean, trace? It means that you have trace on all finite group algebra finite group, and trace on finite on this algebra is nothing but the character of the group. So the problem about characters on symmetric group, for example, reduced to the problem about central measure and vice versa. Yes. Let me finish one. Of course, trace could be indecomposable. Space of all traces. Well, if we decide to normalize trace, then a set of all traces on sister algebra is just convex compact. And the main interest, of course, is extremal point of this simplex, which is indecomposable traces. Traces which can't be represented as convex combination of other traces. Indecomposable traces, or in terms of group, indecomposable character corresponds to ergodic measure. It means that in our definition of central measure, we also can, this is also convex compact of all invariant measure, and indecomposability means that you can't decompose central measure to the convex combination of other central measure. This is what I called ergodicity, and let me explain later why it's ergodicity, but nevertheless we have correspondence. Indecomposable character, for finite group this is irreducible character, but for infinite group it doesn't mean irreducibility from one side, and ergodic central measure, please.
Sorry, I just wanted to confirm. So is there a unique central measure, which is the Plancherel measure the unique central
No. This is what I will tell about as one of example. The set of central measure is complicated. This is our goal, to describe all central measures. For Young graph, of course, there is a well-known Plancherel measure, but let me give you an example. But in order to be more concrete, let me solve the simplest problem. To describe all central measure for Pascal graph. This is very fruitful exercise. Suppose as Bratley diagram we have Pascal graph, infinite Pascal triangle. Oh, here it is. This is they coincide till the third floor, and then on next floor it will be different. So how to describe central measures on Pascal graph? Let me solve this problem. First of all, what does it mean, set of passes on this graph? Well, it happened that this is the same set of passes as here. Graph is different. But set of passes, again, is just nothing more than product of 0, 1. You go to the left or to the right. So this is. Now the difference to describe what does it mean central measure. Here central measure by definition is Bernoulli measure. No problem. And here, what does it mean centrality? It means that if you consider a sequence of 0, 1, which is pass, and suppose two sequences coincide starting from this point. So what you can say about these two guys? Only one thing, that they finish in the same vertex. But what does it mean? It means that you have the same number of ones and same number of zeros. Yeah, indeed, yeah? If you have vertex which is just number of passes Cn of k, so it means that you have k goes to 1 with 1 and k. And what does it mean? It means that you want to describe all measures on the sequences of 0, 1 which has the same probability on the set of finite set with the same number 0, 1. Which means, by the way, that this measure is invariant with respect to change of coordinate. Because if U2 sequence has the same number of 0, 1, then there exists element of symmetric group which bring one sequence to another sequence. So we have the following classical problem to describe all measure on this sequence 0, 1, which is invariant with respect to symmetric group. This is well-known problem which posed by De Finetti in 20s, and the answer is, of course, very well known, that if this measure is ergodic, indecomposable, then this is Bernoulli measure. So the answer is the following: P 0, 1, and measure is just goes to the probability P to the left and 1 minus P to the right. And this is all ergodic measure, all decomposable. So, by the way, it means that we describe all ergodic central measure, which means that we describe all characters of algebra which generated by Pascal graph. But the previous speaker, not maybe the before, mentioned about algebra which so-called algebra of canonical anti-commutative relations. So Pascal algebra which generated, which corresponds to Pascal graph, can be easily described in terms of canonical commutative relations. So this is very nice illustration of the connection between different things. So interpretation of algebra A of Pascal is well known. It's possible to find it in the textbooks, and this is indeed has a connection with algebra of matrices, is algebra of canonical anti-canonical relations. So this is example, and we solve it. But situation much more complicated for serious graph, and my goal is to tell you about new method which can be suggested in order to solve this problem. But before, let me mention that parallel theory of this. So in a sense, I connect two theories of traces or characters and theory of central measure. But I mention also geometrical theory of graph, of simplices. Yeah?
One question. So the term ergodic is applicable only in this case of group algebras, is that correct?
Ergodicity of measure. What does mean ergodicity of measure?
Of the central measure.
Sorry?
To talk about ergodicity of central measure, you need a group action, right? In general, you don't have...
No, ergodicity of central measure is the same as indecomposability. You can't represent your measure as convex combination of other central measure. But more directly, it's possible to describe as follow. I didn't tell about, but of course, if you want, it means the following. Here we have some hidden group action. Namely, this is you can change beginning of the path. I defined many years ago the notion of adic transformation. This is simply one transformation which works as changing of the beginning of the path. I have no time to tell about this, but in this spirit, ergodicity means ergodicity of that action. But don't miss this action with action of this group. It's completely different. This is in a sense Fourier transform. With respect to this group, the Young graph is just the dual object. It is a graph of representations. I remain that representation sense of the Young diagram in sense of symmetric group is just parametrization of irreducible unitary representation. So we have, as I told, we have some action of the group or pseudo group with change of the beginning of the path, and the gradicity means just the ergodicity of this action. So let me return back to very nice theory, which it's elementary theory, but nevertheless, I think that nobody pay attention to this. So I want to say that what I told before can be retold by very simple object, namely, let's consider simplex. Simplex generated by vertices of so let's gamma sub n, nth level of the graph. You have finitely many vertices, and let's consider simplex in R n. Sorry, R. Okay, let me say K. Simply set of all so we have simplex corresponding to each level, and also we have projection of simplex of K plus 1 to K to K. Why? And this is important things which I must tell you maybe in more detail. The projection of simplex is the following. Okay, let me start from general definition and then I give you the example. Graph gamma called equip graph. If for each vertex you define probability of edges which goes to this vertex, say this is V, P V1, P V2. So on each vertex you have additional structure, additional data, namely the probability to reach this vertex from previous level. This is I called equipped graph. The simplest example is the following. If you look at the path from the beginning to given, then you can multiply all this probability over all passes. So equipped structure is canonical if this is product of all these guys are the same, which means in a sense that probability of all passes goes from beginning to given path, given vertex is equal, central measure. So centrality of measure can be described in this spirit. More concretely, let's consider probability of goes from this part to this and from this part to this proportional to number of passes goes to this vertex and to this vertex. It's very easy to check that this is just that rule which gives you central measure. Let me say again. These two guys, P1, P2, maybe more, can be found from the following procedure. Each vertex proportional to number of passes which goes from this vertex to, we have given vertex, and some previous U1, U2, UK. And centrality corresponds to the following equipped structure. Probability of all these edges proportional to number of passes which goes to this. it's easy to check that in this case product will be the same. So centrality is a very special case of the structure of equipped graph. And we can say about centrality without this notion, because it's I already told what does mean centrality. But now I want to make more general definition, namely to define equipped structure of equipped graph. Now our simplex, let me write down, simplex corresponding to nth level can be produced, maybe as it's, well, I can't write down three-dimensional simplex, but it's possible, of course. So the connection of equipped structure with my projection is the following. I have this vertex, and I have projection, and if I have, say, Pn, and the projection of this vertex has so-called, what's the name? Coordinate in the simplex proportional to the distance. Huh? Yes. What's the word? Huh? Barycenter, yes. This is barycentrical coordinate. So each vertex can be considered by its barycentric projection of the vertex can be considered as barycentrical order. So this is just what we have equipped graph. So in a sense we have projective limit of the simplices, and this projective limits, my claim, and this is not so difficult, this is just the set of all measure on the space of passes of the graph which have given this probability called co-transition probability. Why co-transition? Because if you have Markov chain, and this is of course Markov chain, you can say, okay, from this vertex we go with probability 1, probability n. This is transition probability. Here I define co-transition probability inverse, which is more important in our situation. If we have vertex, with what probability we go from this? So we have system of co-transition probabilities, just gives you a structure of an equipped graph, and in the same time it defines inverse limit of the simplices. With respect to these projections. And my claim, we join this pure geometrical theory. You can define this projection without any graph, so you can say what's the barycentrical coordinate of each vertex. And you can say this is limit. My claim is that this is a limit of all measure on the space of graph which has given co-transition probability. What does it mean, given co-transition probability? It means that if you consider this measure, fix some path, and look at the conditional measure on the beginning of the path, then this conditional measure defined by this co-transition probability. For example, central measure is just nothing more than set of central measure is just the example of such a things. And what kind of example? In our case, it's very simple. You have this vertex projected to the previous vertices with probability, as I told, proportional to the number of passes. So for the central case, you have very concrete procedure for co-transition probability, and this gives you the limit. So we have the third language. Set of all central measure is nothing more than inverse limit of simplices. Ergodic measure is ergodic measure of the simplices, and so you can again look at the unfortunately I don't know many paper on this direction, but this is very simple object is a Choquet theorem for simplexes is almost trivial. You have unique decomposition which corresponds to ergodicity and so on. Nevertheless, this is very fruitful idea, and I can realize this idea even on example of the Pascal graph. It's very easy. For Pascal graph you have, okay, I think that no sense to spend time on this. Anyway, there is a simple example in which this is a visible picture, but for more general it's not so trivial. So let me now formulate the main result, because I didn't formulate any theorem. I consider only the part of the several applications, but not theorem. The question which I want to solve, namely to to classify graph, or if you want AF algebra, on algebra in which the problem about invariant measure is regular, can be solved, and more and in the case when this problem is has some flavor of flavor of the problems which has no good answer. For this, let me mention the following, that the problem of the description of even central, but let me say the following, the measure which corresponds to given equipped structure will be called compatible measure, compatible with given equipped structure. But even for central measure, description of central measure includes the following problem. Problem of invariant measure for actions of amenable group. Why amenable? Because all our theory consider so-called hyperfinite equivalence relation, which is a limit of finite equivalence relation. But non-trivial claim that each problem about description of action of some group, amenable group, problem with respect to given levels. And so it gives you some, in the limit, it gives you some sequences of metric space, and the Choquet boundary of the simplex, or the same set of all ergodic invariant measures, will appear as some limit metric space. And the procedure of this, based on some very important and very simple method, which I called as transfer of metric. Now let's consider two adjacent levels of our graph. Suppose you already have some metric rho n on finite space and finite metric. I want to project this metric to the next level. This is a part of the following problem. You have some set, say X, and you have some map to another space, and here you have metric. How to define metric here? No any canonical way. Metric can't be projected along some map. Even if you have fibration, if you have simply this case, if you have metric here, how to define metric here? It's impossible. But it's possible if you have somewhere the following. You have conditional measure on preimage of each point. So you have y, you consider some points, and this is projection pi, and look at the preimage pi of y, some subset. And suppose you have some conditional measure denoted to mu a. Then you are in the following situation. You have metric space, and you have some measures, and then you can define, namely, transportation metric or Kantorovich metric, how to define distance between two measures if you have distance on space. Probably you know how to do this. This canonical, classical method of Kantorovich is the following. In this case, so you have metric space, you can define so-called product of this. For example, I want to define distance between these two measures. I consider product. This is one, this is another. I consider so-called coupling, measure on the product which is given marginal. And then consider mean infimum of mathematical expectation over this psi joint distribution of rho xy. This is by definition distance between mu y and mu y prime. Everybody who listens lecture on linear programming know that if you have finite space, you have transport problem, then you can define the cost of your transportation problem, minimal cost, and this is just this metric. So my claim is the following. If you have metric on this space and you have conditional measure on preimages, then you can consider metric here. Namely, distance between two metric is distance between corresponding measures. So let's apply to this. So you have 2 points, V1, V2. And remember, you have equipped or co-transition probability. This and this. But here you already have metric. So you can consider distance between two measures and say this is measure and this. So we define for all equipped graph sequences of procedure how to describe measure from nth level to other level and so on. I want to say from the beginning that it's better to consider more general situation when you have metric not only on this level, but metric on the all infinite passes which started from here. And then you define metric on all passes which started from here. Why it's important? Because this, my example, can say that we obtain zero. For example, if you have two vertices with the same previous, so it becomes zero. So it's better to avoid this case. Theorem. And this is goal of my lecture. Theorem definition. graph, Bratley diagram, called standard, if this procedure started from some initial metric and step by step consider the new and new metric, has a limit. So sequence, sorry, I want to say that it's better to say not metric but semi-metric, because sometimes it can be zero distance. But you have sequences of semi-metric spaces, namely space of all passes, and the claim is the following. Suppose these sequences of metric, semi-metric, tends to some semi-metric, maybe to trivial metric. Then I call that my graph is standard. And this is a definition part of the talk, of the claim. And theorem part of the claim is the following. This is just metric on the space of all ergodic central measures. So set of all central measures appears as limit metric spaces. And if graph is of this type, and we have a collection of this graph, so you are lucky, you solve this problem. Of course, it doesn't mean that you know answer as evident way, transparent way, because you have to calculate this metric. But nevertheless, this is a method. If you have no such a space, and it's possible that you have no limit, then you have more complicated situation, which occur very often. It's the rule. I will not speak about this now. I have no time. But fortunately, Young graph and many-dimensional Young graph and so on are not in this case. And final corollary. This is so-called limit shape theorem. If graph is standard, it means that you have limit shape theorem in the following sense. What does it mean, limit shape? Limit shape theorem is a theorem about some configuration which concentrated near one configuration. For example, for our well-known example with Kerov and another guys who found it, Shep and Logan, to look at the Plancherel measure, central measure, and it happened that there is a one curve such that in epsilon neighborhood of this curve, we have all Young diagram, almost all Young diagram in neighborhood of this curve. The theorem is the following. If graph is standard, then for each epsilon, you can find such a n that if n more than n, then all passes which has measure more than 1 minus epsilon will be on the level n near the one vertex, epsilon neighborhood of one vertex. Where, in what sense? In that sense. So all passes will be around one vertex in the sense of that metric, which of course you can have to find. Nevertheless, this is the simplest form of limit shape theorem. Really, it depends on this metric, and you can refine this metric, but nevertheless, this is a situation. If you have not standard, there is no such a theorem. And this is very important, close to a problem which probably I will mention tomorrow, namely when I will speak about filtration. Really, what I told you, this is the same as study of filtration. So these two things, simplices and space of passes, just the following, that standard graph gives you some also restriction on the structure of Choquet boundary of the simplex. Maybe you know the Choquet boundary could be very complicated, can be everywhere dense. This is so-called Paulson simplex. Paulson simplex is simplex for which not linear convex combination, but vertices, extremal vertices itself generated everywhere dense set. So Paulson simplex is just example when you have no such a. For standard case, Jacquet boundary will be closed, and this is very good case. So all these different kind of languages coincide in this notion of standardness. Namely, this is a good case in any cases. Thank you. I apologize. Maybe I mentioned many different things, but nevertheless, maybe last part will join all this. Yeah?
So you mentioned the converse of this standard thing, that if it is not if a central measure is not standard, then you do not have a limit shape. But what if a measure is not central?
Well, I can give you, yes, this is a good last example, because I try to convince you that standard is very good and it's true. But what is not standard? I tell you, let me, and this is a very good, how to say, challenge. Look at the Bratley diagram, which nobody considered, I think, which I called graph of ordered or unordered, that's not important, pairs. That's a very simple picture. You have vertex. On the next level, you have 2. And the induction rules the following. The n plus 1 level is nothing more than all possible pairs of previous level. Or, by the way, including the twice mention of given vertex. So, for example, here you have, let me write down. So you have 2, then you have for unordered 3, for ordered you have 4, then again, so each time you get together all pairs. Set of vertices grows exponentially. This is example of Bratley diagram, some algebra, which is not standard, which has no any limit shape theorem and so on. But nevertheless, it doesn't mean that you you didn't need to study this. It's very important, and there is a situation, ergodic situation, in which this is important. Yeah.
So is there some way of looking at the graph and seeing if it's to be a standard?
Yes. This is a way. This is what I want to say. This is a way how to distinguish all graphs on 2 very roughly, of course, parts. Standard, when you have regular behavior of all this picture, and all other. But of course, I have to say something about non-standard case, but in this case, I have to work with what I mentioned yesterday about the classification of metric measure space. In this case, it's just we need some new information about, but this is possible to say something. But of course, standard case is a good case, and the problem is how to check that your case is standard. This is non-trivial problem even for young graph, because transparent calculation of this metric is still open question. I know that they exist, but nevertheless, I want to have formula. It's not so easy. Maybe there's no good formula. But of course, this method, I tell you that for young graph, we have over maybe 5 now proof of theorem about list of characters, starting from classical Thoma formula, from which we stand our proof with Kerf and some other. But up to now, we have no pure combinatorial proof. And this is pure combinatorial. it doesn't finish in a sense, but pure combinatorial, because what I mentioned before has no any information about symmetric functions, and so this is pure combinatorial information about Young graph and so on. Thank you.